This section is about modeling with equations, which means we want to take a real-world scenario and come up with a mathematical model that's going to explain essentially what's happening. So here's some strategies for whenever you're working with word problems, because I know they make us a little bit nervous. I'm not going to read through all of them, but the couple things that I want to point out is step one, read the problem carefully several times. I will read a problem at least 3 times when I'm going to work it, and I work with a different purpose each time. So the first time I'm just trying to get kind of a general idea of what is happening. The second time I read through, I'm looking for those specific pieces of important information. And then the third time through, I'm reading to really make sure that I understand what the question is asking and what my goal is with that problem. Step 2 essentially is to define your variables. And that's a piece that we often skip, but it's, in my opinion, the most important step, because once you take the time to really identify what your unknowns are and define what they are going to represent, it often becomes much more clear what your equation should look like. Then you're going to essentially solve the equation, and the last step is also very important. Make sure that you always go back and check your solution in the original wording of the problem, okay? X equals 7 does not usually answer the problem given in the situation, so you will need to make sure that you figure out what that 7 represents, what are the units, and how to describe what you have going on there. Okay, we're going to look at just a few different examples today of some different types of word problems using the types of equations that we know how to solve so far. So example 1 says the bar graph in the figure shows the 10 most popular college majors with their median or middlemost starting salaries for recent college graduates. The median starting salary of a business major exceeds that of a psychology major by $8,000. The median starting salary of an English major exceeds that of a psychology major by $3,000. Combined, their median starting salaries are $116,000. We want to determine the median starting salaries of each of these majors with bachelor's degrees. Okay, now, we could probably estimate this information from the graph, but the scale here is not so precise that we can figure out exactly what it is. So that's why we're going to use algebra to do this. So when I read that problem, I see that I've got multiple different majors. I see that both the business major and the English major are described in terms of a psychology major. Psychology is what they're being compared to. And then I see that the question that I'm trying to answer is what are each of their starting salaries for each of these majors. So because everything is described in terms of a psychology major, that's what I'm going to let my variable be. Since the other two are described in terms of a psychology major, we don't need 3 variables. We can use the value of P to determine the other two. So we know that a business major makes $8,000 more. So we can call that P plus 8. That's going to be the salary of a business major. And then an English major makes $3,000 more than that. And that might seem kind of weird, but if you want to do anything with a degree in psychology where you're going to make some money, you're going to need a master's degree or a doctorate degree. So that's why psychology majors don't usually start off making a ton just with a bachelor's degree. Okay, so we've defined our variables. Again, we want to find all the salaries. Now, that means I'm going to need some more information because I've got to be able to set up an equation here. And it tells us that if I combine all 3 of their salaries, I get $116,000. So the equation that we're going to set up is going to be P plus 8 plus P plus 3 equals 116. That's each of these salaries combined equals 116. So to solve this, let's combine our like terms. We get 3P plus 11 equals 116. So 3P equals 105. Whoops. And that means that P must be 35. Now again, we've solved the equation, but we have not yet answered the question. So again, the question is, determine the median starting salaries of psychology, business, and English majors. So to answer our question thoroughly, we need to use those variables. So a psychology major is P, so they make $35,000 a year. A business major makes $8,000 more than that, so if we add 8, we're going to get $43,000 a year. And an English major makes $3,000 more than the 35, so that's going to be $38,000 a year. And so that answers the question, and now we're done. So that's kind of a model of using those steps. Okay, let's look at a couple more in different types of situations. There's a couple of important things to notice here on number 2, even though the math isn't particularly hard. So it says researchers have surveyed college freshmen every year since 1969. The figure shows that attitudes about some life goals have changed dramatically over the years. In particular, the freshman class of 2009 were more interested in making money than the freshmen of 1969 had been. In 1969, 42% of first-year college students considered being well off financially either essential or very important. For the period from 1969 to 2009, this percentage increased by approximately 0.9 each year. If this trend continues, by which year will all college freshmen consider being well off financially as essential or very important? Okay, the first thing that we need to do is define our variable. So the question is asking us by which year. So the variable that we need, the unknown amount, is going to be talking about time. So in this case, I let x equal the years. And it can't just be years. It can't be the year 1969 is the year that we're in. But remember, if you use that, that stands for 1,969. That won't work to have that be plugged in for our variable. So we need to figure in 1969, that's when they first started counting, and then we measure time after that. So typically, when you measure time in a problem, you want to have a starting point that is time equals 0, and you want to measure your time in years since that starting point, which in this case is 1969. That's almost always how we need to define time in a word problem, okay? So, in 1969, 42% said that they thought it was essential or very important. And then they told us that it changes by 0.9 each year, okay? Hopefully you're recognizing this as a linear relationship. If it increases by the same amount each year, that's a constant rate of change. And then the question is, what should this equal? Well, we're trying to figure out when all college freshmen believe that. And so that means we want to get to 100%. Okay? Now, when you solve this equation, which I'm confident you can do, we get that x is approximately 64.4. Now, again, the question said, by which year? So it's not after how many years, it's by which year. So now we need to convert back to a year, like a specific point in time. So let's use then that we want to get to the 65th year since 1969. That opinion is going to change somewhere in the 64th year, but it's not going to be until the 65th year that we actually start seeing a difference. So 1969 was when we started, and we want to add 65 years to that. That takes us to the year 2034. Okay? And so the answer would be in the year 2034, which we're coming up on sooner than we think. Whoops. Okay. All right. I'm going to skip example 3, but I will post the notes so that you can go ahead and look at that on your own. Here is a reminder of some of the common area, perimeter, and volume formulas that you should be aware of from geometry. These are formulas that you should know on your own without being given. And so let's look at how we might use those in a couple of word problems. Number 4 says, the length of an American football field is 200 feet more than the width. If the perimeter of the field is 1,040 feet, what are the dimensions? Now, they either told us about the length or the width. They told us the length is 200 more than the width. So width is the one that we know nothing about. So that's what I'm going to let my variable be. Let's let W equal the width. And we're measuring in feet. That's always important to remember. And so if W is the width, then that means W plus 200 is the length, again, in feet. Okay, so here's what we're looking at. We have our field, and we know that the length is 200 more than the width, and then the width, and we know that they're the same on both sides. So they've told us then about the perimeter of the field. Well, we find perimeter by adding up all of the sides. So we have 2 W's, one on each side, plus 2 W plus 200ths, one on each side. And when we add that up, we get 1,040 per the problem. Now again, I'm not going to go through and solve this, but when we solve this, we get that W is equal to 160. So go back again. What was the question? If the perimeter of the field is 1040 feet, what are the dimensions? So that means we want the length and the width. Well, the width is going to be 160 feet by 200 more than that, which is 360 feet. And so there we go. Now, number 5, we're going to go ahead and skip for this unit. We'll come back to problems like this when we look at quadratics later. But the last one that I want to look at is one where we're going to use the Pythagorean Theorem. I'm sorry, I take that back. This one is the height of a cone. So I'm going to skip this one as well and let you go ahead and take a peek at this one in the notes that are posted. But I want to look ahead and see a problem with the Pythagorean Theorem. So you recall the Pythagorean Theorem from geometry and 7th grade math and algebra 1. You've seen this lots of times. So if you have a right triangle, the sum of the squares of the two legs, a squared plus b squared, is going to be equal to the square of the hypotenuse. So let's look at this last example. It says a wheelchair ramp with a length of 122 inches has a horizontal distance of 120 inches. What is the ramp's vertical distance? So let's start by drawing a picture of what we have here. So we have a ramp that looks something like this, and we know that the length of the ramp is 122 inches. All right. It also tells us that the horizontal distance, so that's going to be this bit right here, the horizontal distance is 120 inches. And we are trying to find the ramp's vertical distance, which is going to be this right here. So hopefully you can see how this is going to fall into the Pythagorean Theorem category. So we are going to have 120 squared plus x squared equals 122 squared. So we get that x squared is equal to 484, and then we square root both sides, which typically would require a plus or minus, but we can't have a negative distance, so we only need to consider the positive root, and we get 22. So that means the vertical height is 22 inches. The last part of the problem has us interpret this information a little bit. It says construction laws are very specific when it comes to access ramps for the disabled. Every vertical rise of 1 inch requires a horizontal run of 12 inches. Does this ramp satisfy the requirements? So it cannot be steeper than that. So what that means is that we need to know, is our ramp, which has a rise of 22 and a run of 120, think of it like slope, that's exactly what it is. We need that slope to either be less than or equal to a rise of 1 and a run of 12, okay? Now, 22 divided by 120 comes out to 0.183, and 1 divided by 12 comes out to 0.083. And so this inequality is not true. So that means that the ramp that we are looking at is too steep, and it does not meet the requirements. So you've just got a little bit of practice with different types of word problems. They're not all exactly the same. Just go through, read with purpose, read more than once, collect your information, draw pictures that if you need, and set up an equation, and you should be able to get them all pretty quick.